And then that gives you sort of an idea. And oftentimes I might ask you, for example, a worst case analysis. Typically when the algorithm gets more involved, I'll ask you for worst case or best case. Best case is too easy. What's the best case? Go from A to A? Okay, done. Or from A to an immediate neighbor. But anyway, all right, any other questions about this? Anything else? Okay, so the next algorithm that I want to go over is something called least cost path. And we mentioned it on Monday. And there are a couple of famous algorithms. This is a pretty famous algorithm. I'm not even sure who came up with this particular algorithm, but it's so easy, I like to cover it. Then there's another algorithm called Dijkstra's algorithm. It's a little bit more complicated, so I'm not going to cover it, but I can discuss it if we have time. And then this one, Dijkstra's is also pretty straightforward, actually. But this one is, I like this one a lot. So basically, what we have here is we have a digraph. And you can see that this is a new digraph. And this digraph has a bunch of edges. Notice that E can go to F, F can go to E. They're different costs, whatever, that's fine. We're looking for a least cost path between two nodes. Let's say I want to go from B to C, I want the least cost path. Okay, it's a relatively simple graph, but you can see A has a lot of possibilities. A goes to B, it goes to D, E, and F. So it goes to B, D, E, and F. Notice that in the adjacency list, I not only include the neighbor name, but also the cost. So you can see that A can go directly to F with a cost of 5. And that's seen right here, 5. I can go directly to D with 4. That's seen right here. So these are all the neighbors and the costs. So you can see that A has 4 connections, B has 2, C, D, E, etc. So now we want to be able to calculate the cheapest path, the least cost path, from any vertex to any other vertex. Again, if we do not reach the vertex, in some cases it may be impossible to reach the vertex. I'm not sure there's any such vertices here. Let's see. No, I think we can, because you can see over here, see this over here? The big fat cycle. So in the worst case, you can just make a big circle and get it. But it may be possible. For example, if I took this arrow and I changed it in this direction, put it this direction, then that might change some things up. For example, if the arrow was going in this direction, could C reach A other way? If you go here, couldn't get to A. So therefore, the algorithm would terminate because we would have no more choices somehow. And if we have no more choices, then we would terminate the algorithm, and if the path has not been found, there is no path. There's no path, there's no least cost path. Okay, so here's the algorithm, and I'm going to look at this algorithm, and then we're going to discuss it, and then we'll show us a very specific example, which will make it very clear. But this is the idea that we have here. So we're going to have 2 columns in this algorithm. One column will contain all the possible paths. These are paths that have not been ruled out. And the right-hand side will contain paths that have been verified to work. So if you're going to go from start to destination, then anything on the right-hand side is actually a path that goes from start to destination with a particular cost. And it's not enough for us to just find it, we have to find the least cost. So this is a little bit more difficult because we may have to visit the same node twice on 2 different traversals. And the longer one may be the cheaper one. So we can't throw it away. Simple. Okay, so we have 2 columns. On the left-hand column, we have possible paths. So I'm going to say possible path. And on the right-hand side, we're going to have paths. Paths that are actually paths that we have determined for a particular cost. So the path list and the possible path list, the possible path list goes to a 0 cost and includes a single node. And the path of that one is simply a destination. So for example, if I want to go from, let's say, A to J, then in the possible path, I'm going to have the fact that I can reach J with a cost of 0. Why? Because if I start at J and I'm going to J, I can get there plus zero. And so I'm really going to be looking at predecessors. Not just predecessors of individual nodes, but predecessors of partial paths. So I will start the first possible path, let's say at J, with a cost of 0. There are no actual paths. So let's say I want to go from A to J. So now what I'm going to do is, again, I'm going to set the possible path to 0 cost with a destination node only. Then I'm going to set the path list to nil, which means an empty, the right-hand column has nothing in it. I'm going to use some kind of a Boolean indicator which says I'm at a dead end. I can't go any further. So dead end sets it's equal to true, and we'll make it untrue as soon as we have some possibility. You can see dead end is going to get set equal to false under some conditions. So what we're going to do is we're going to say for each path in the possible path list. How many paths do we have in the possible path list so far? We have a single possible path, and that is destination node for cost of 0. So in this case, for one possible path, we are going to now iterate over each node in the graph. For each node in the graph, we will think of this possible path with a destination. We'll think of the node, the first node in that possible path, as a lead node of that partial path. So initially, if my node is J, the lead node of the possible path is J. Why? It's the first one. Well, it's also the only one, but it's the first one. So therefore, it's the lead node. So I'm going to consider that, and I'm going to take for each node in the graph, if any node in the graph can move to a lead node, meaning if I can go from another node, A, B, C, D, E, F, G, H, I, if any of them individually through this loop can go to J, then create a new path by inserting this node. Notice I've highlighted the word node, so you know it's referring to the same one. So node right now is going to be any node in the graph. I determined that this node can move to my lead node, which is J, as an example here. Therefore, I'll create a new path, and this new path actually will be a possible path, I should say. New path by inserting this node as the new lead node. So if I find out that C can go to J, then I will have a CJ possible path. And C will be the lead node. Why? Because C can go to J, and it's the first one in that partial path. So I'll create a new path by inserting the node as the new lead node. Because I have added a possible path, I'm setting dead end to false. Because there's going to be at least one thing to go. I will now set the cost of this particular path equal to the cost of the original by adding the cost from our node to the old lead node, which means the cost from, let's say J is the destination, let's say D can go to J. The cost from J to J was 0, so the old cost was 0. Let's say D to J is a cost of 5. The path from D to J is 5. And now it has two nodes, and the lead node is D. The lead node is whatever node is. Okay, so you understand I'm going to go through all of the nodes in the graph. And I'm going to try to find a node that will go to a lead node of a possible path. And if I find one, I'm going to create a new possible path, inserting this node, pointing to the new lead node. So the new possible path will be one longer than the possible path I just took out. The cost will be updated for all of them. Now I will check before I go on to the next node in this loop iteration. I will check if the new lead node that I just put in, this new lead node becomes, this is the new lead node, right? I will find out if the new lead node is equal to start. Because if it does, what does that mean? That means the lead node of the partial path actually is now a full complete path. So if the new lead node is equal to start, move the path into the path list. Okay? Sorted from least to high cost. That means insert it into a list of already done paths. so that it fits in an ascending list of paths by cost. If there's a cycle in the path, that means if you had a possible path, and the lead node is K, and you said D can go to K, and you added the cost from D to K to the cost from K to the destination, which is so far so good. If you find, what node did I say here?
D.
So if I find that D was added as a new lead node, but then I scan and I see there's a D here, there's a problem. That means there's a cycle. I will remove that from the possible path. That one's done. Because I'm not going to accept the cycle, because the cycle, there's no way you're going to have a cycle and have a minimum cost. Because unless the cycle is free, you've increased the cost without the cycle to get to the same node. There's a cost to go from the start of the cycle to the end of the cycle. So just don't go to it. Okay, and so I'm going to do all this stuff in here. These are all of the, okay. And then I'm going to say, I'm going to do this loop again, but I will not repeat it. I will do this until the possible path is equal to nil. What does that mean? There's no more possible paths, or I have a dead end. So if the possible path is not equal to nil, that means I still have some paths on the left-hand column. Or dead end, and dead end is going to be gotten how? When does dead end get set equal to true? Well, it gets set equal to true here. And it gets set equal to false when? As long as we have a new possible path. So this dead end business is just making sure that we have a potential to start the algorithm. That's all it is. Now, if the path list is nil, when we terminate the algorithm, then there's no such path. Can't reach it. Else, we'll choose the first path on the right-hand column. It's going to have the least cost. Why? Because we're moving it into the path list and we're sorting it by cost. Every possible path has a cost. So once I insert into the possible path and I connect to the lead node here, because the possible path has a cost and the connection from this node to the lead node has a cost, then the path, if this is a path now, goes on the right-hand side, it has a cost. So it joins the other path with a cost, and it gets put into it according to increasing cost of these paths. Okay, so let's take a look at how this is going to work. How this is going to work and how this is going to look. So initially, so again, this is the algorithm. So initially, the possible path list, this is our left-hand column, this is our right-hand column. So this is, again, this is going to be based upon our graph. So we want to go from, I think we want to go from A to E, right? We want to go from A to E. So the first thing we do is we put in a potential or a possible path starting at E, which is the destination. The cost of that, if you start at E and you go to the destination, is 0. There are no possible paths at this point yet. No actual paths, rather. So now what I'm going to do is I'm going to go to the loop iteration. And notice what I'm going to do. So this possible path to E in the iteration gets converted to 1, 2 possible paths, and an actual path. So we get DE, FE, and AE. Let's take a look at the graph again. So this is a cost of 0. We're trying to go from here to here. So this is a possible path. So we notice that the in degree into node E is what? What's the in degree into node E? Well, the in degree into node E was obviously what? All you have to do is count all of the nodes that can go to E, which is 1. What is it, 2? 2 and 3. So therefore, since 3 nodes can go to E, specifically A, D, and F, they all become possible paths because they're all nodes that can go to E. So therefore, there is an AE, there's a DE, and there's an FE. Notice that DE has a cost of 2, FE has a cost of 1, and AE has a cost of 7. Notice that the new lead node in AE is A. Therefore, we'll move AE into the path list, which is initially empty, and the cost of 7 will become the first path, and that's what we have here. And that's why AE has been moved immediately to the path list, because it starts with the start and ends with the destination with a cost of 7. But I have other possible paths. You can see D to E and F to E will cost of 2 and 1 respectively. So now I am going to consider, so this is the lead node of this possible path, this is the lead node of this one. So I'm going to take this path out, and I'm going to find every other node, A, B, C, D, E, F, G. Oh, forget about D, right? We don't go D to D. I'm going to take every single node other than D, and to see if I can connect to D. And for every such possibility, I will have a new lead node going to DE. Notice that I have a DE here that was generated because B can go to D with a cost of 2. Why am I asking you this? Why am I stopping on this? Because if you answer my question correctly, then you understand what I'm talking about. And if you're like, I don't know, well, you can see that DE had a cost of 2, and now we have B and DE cost of 4, therefore the difference between this cost is 2, correct. Notice that we have another path, which is DE is also here, because A can go to D. A can go to D with a cost of 4. And as soon as A goes here, notice that goes into the path list with a cost of 6. So how many nodes go to D? What's the in degree of D? The in degree of D can be, you can see it here, it's going to be whatever goes to D, so we're going to have 1, 2. So we have 2 as an in degree to D. So we have 2 paths that end with DE. This one and this one. This one is moved to the path list because it also starts with A. This one stays in a possible path list because it doesn't. Now, we also have another path, FE. Now, what's the in degree of F? In degree of F, we have 1, 2, 3. So into F can go A, C, and E. A, C, and E. So notice that A, C, and E. Notice that FE is the end. So C can go to F with a cost of 5. And also E can go to F. But this path is quickly removed because it creates a what? E can go to F, but F is already going to E in this partial path, so therefore this is done. That's going to get removed. But also, A can go to F. Since A can go to F with a cost of 5, notice that these two become paths. And their cost is a little bit lower than the cost before. So now we have 3 paths, and we have 3 possible paths. Well, actually 2 possible paths. So notice that 7, 6, 6 exists here. Now notice that this path that's remaining here is BDE. Notice that BDE is here, which means we took this path out and we found what? We found that A can go to B with a cost of 1, and that moves it into the path. It also moves it as the best path so far. Okay? CFE, notice that CFE, CFE we have F goes to C. But that creates a what? Creates a cycle, this path is gone. So therefore we have no more possible paths. So now we go over here and say, do we have paths? And the answer is, yes we do. And what is the one with the least cost? A, B, D, E, that's a cost of 5. So the least cost path will be selected from the right-hand column, one that has the least cost. Now you understand that if I had, for example, changed the graph, notice that A to E was a very expensive path, but it was very fast, right? Only one edge. I could have made the cost of this, for example, 4. If I made the cost of this to 4, what would happen here? Then this would be 4. But everything else would still flow the same way. But it's just that A to E, our cost of 4, would always be the lead cost. So even though it came up fastest, it was still the best. In this case, it came up last. The best path came up last, but it could come up first. The other paths are still going to come in. Okay? So that is an example of a least cost path. Any questions about that? If the average number of edges in a graph is 2, and I have 10 vertices, then how many edges do I have? Can multiply as well as the next guy. So we have 20 edges. So that means, on average, if I have 20 edges and 10 vertices, what is the average number of edges per vertex? 2. Why am I asking these questions? Because this is the kind of logic that you need to be able to think. If I give you some kind of example, like I want you to see how many operations are going to happen, how many comparisons are going to happen, how many possible paths are going to happen, how many paths are going to happen before we start hitting cycles. Keep in mind that a path with 10 vertices cannot be any longer than what? Let's say 9. Because if I start the destination, 1 will give me the second one, 2 will give me the third one, and 9 will give me the 10th one. That's the longest path I can possibly have. That could be the least cost path. Could be. So that means that paths cannot go any longer than n minus 1 in the worst case. Any path cannot go any longer without either becoming a path or becoming a loop and being thrown away. All right, so anyway, those are good homework questions that I'm going to be coming up with for you guys. All right, any other questions about this so far? Good? Not too hard? Not too bad? All right, let's take a look at, I want to go into another type of algorithm. So now we're going to switch a little bit and we're going to think about algorithms that deal with strings. Okay, this is the algorithm we're going to look at is one of the most famous string algorithms there is. It's so complicated, it took 3 guys to come up with it. And they came up with a clever name of KMP, which is their letters of their last names, stands for Knuth, Morris, and Pratt. All 3 of these guys are big-time algorithm developers and famous. The most famous one is probably Knuth. Donald Knuth. He came up with unbelievable, interesting algorithms. So KMP, Knuth, Morris, and Pratt is an algorithm that talks about searching for strings. And it is still the best algorithm, by far, of this type, and it's being employed for searching, finding things inside documents. You have a document of 25 million characters, and you're looking for Joe. Where's Joe? Okay, so that's the idea here. So we want to find the occurrence of a string within another string. And this algorithm is going to be not very intuitive initially, at all. Well, that's what makes him a great algorithm developer, that he comes up with these bizarre things that make it very easy to implement or to do, but not easy to conceive of. So let's find out basically how, what is string searching all about. So basically, the first idea is something, we come up with the notion of something called a brute force algorithm. It doesn't sound very, very sophisticated. Brute force, right? A brute force algorithm basically means what? What do you think it means?
Try every possible combination.
Try every possible combination. This idea of a brute force algorithm would be very ineffective in cracking a well-designed password. And that's the reason that passwords often require how many characters? Well, I'm talking about real passwords. I'm talking about for super highly sensitive data, what type of password, number of characters we use for passwords. You've heard of multi-bit encryption? So typically we use 256-bit encryption. So if we take 256 bits, if you just use 1 bit, then if that's going to be your encryption, then you can either encrypt with a 0 or a 1. So I'll try everything with a 0, try everything with 1, I'm done. I can do that pretty quickly. If you use 2 bits, now I don't know if you're using 0, 0, 0, 1, 1, 0, or 1, 1, but I can have 4 combinations of 2 bits. That 4, when increased to 3 bits, goes to 2 to 2 goes to 8, 2 to the 3rd power. When I go to 8, it's 2 to the 8, or 256. When I go to 256, it's 2 to the 256th power. Two to the 256th power. Let's see what exactly that is. How many possible encryptions are there with 256-bit encryption? Well, 2 to the 256th power is the same thing as 2 to the 32nd power times 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 2 to the 32nd power again and again, 8 times. 2 to the 32nd power multiplied by itself 8 times. Now, what is 2 to the 32nd power? Well, 2 to the 10th power we know is a K, 1024. 2 to the 20th power is what? Is a meg. And 2 to the 30th power is a billion or a gig. 2 to the 32nd power, well, that's like 2 to the 30th times 2 times 2. So it's 4 gigs, 4 billion, 4 billion. So take 4 billion, which is 4 times 10 to the what power? What's billion? 10 to the 9th power. And take 10 to the 9th power and multiply it by 10 to the 9th power 8 times. That's 10 to the 72nd power. And then take all those 4s, because we have 4 times, multiply it with 4, which is 2 squared, to the 8th power. 2 squared to the 8th is 2 to the 16th. What's 2 to the 16th? It's 64K. So 64K, 64,000 roughly, times 10 to the 72nd power. It's a lot of possibilities. So if you want to crack into pretty much anything, if you want to try all those possibilities, then you're going to do it. And this is called brute force attack. But the problem is, computers aren't, if you actually were to generate each possibility, each possible crack, at the rate of, let's say, 1 million per second, you could never do it within thousands of centuries. So we call those safe encryptions, because brute force is not going to uncover it. You could get lucky, but they are very unlikely to get discovered. So you can see that it's very, very important. So a brute force algorithm basically tries all the possibilities. When all the possibilities are exhausted, we have solved the problem. But if that takes, the length of, the life of a star, then that's a little bit too much to hope for. So brute force algorithms are good for complexities that are low or problems that have higher complexities but are very, very small. I mean, if a problem has an exponential complexity, but n is equal to 10, then 1024, I can do 1024 instructions. But if it has complexity and n is equal to, let's say, 128, then there's not enough centuries. Billions and trillions of centuries will pass before you even have a fraction of the possibilities. So brute force algorithms are good for small problems or very low complexity problems. Otherwise, they are devastatingly bad. Okay, so the initial idea to search for a string within a string is a brute force algorithm works like this. We have a text. So text is a bunch of sequence of characters. I just made it a bunch of A's, B's, C's, and D's. And so because this is text, I call it T naught, which is T0, corresponds to the first character, T1 corresponds to the second, and T11 corresponds to the last one. So, and I'm going to assume that the length of this text is n characters. But it could be, it could be 0 to 11, it could be 0 to n. Text can be very long. Text can be several characters, or it could be, 75 megabytes. The pattern is typically what we're trying to find within the text. So the pattern, let's say, is ACAC, and the pattern is going to be broken up into four characters. We're going to call it pattern naught, pattern P naught, P1, P2, P3, and the pattern length is, let's say, M. And so what we're going to do, literally, we're going to have this text, and then we're going to have this pattern, and we're going to see, let's compare the pattern. Tick, 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 ah. That means I mismatched. So maybe I match. So what I'm going to do is shift by one. So I'm going to keep sliding the pattern. If I keep sliding the pattern by one and comparing all of every character, I will eventually determine if this substring occurs within the text, or determine that it doesn't occur within the text. I need to have, if it's a 4-character pattern, I need to have a ding, 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 ding. No. Pretty straightforward. So, we match P naught to T naught, P1 to T1 until we have a mismatch. On a mismatch, we go and match P naught to Pi and P1 to Ti plus 1. So we simply shift the pattern by one, like we talked about. The worst case is we compare m characters, n minus m plus 1 times. No. So m characters are the length of the pattern. Now, why is it n minus m plus 1? Because it's going to be n minus m. So therefore, the pattern can only come as close as n minus m to the edge. Because if the pattern is 4 characters, but the text only has 3 characters left, you're not going to match it. So you stop a little bit earlier. So you don't have quite n times m. So therefore, we have m times this, which is mn minus m, what is this over? Mn times m squared, should be m squared plus n comparisons. So usually m is much smaller than n, because the pattern is usually much smaller than the text we're searching through. So therefore the complexity could be essentially quadratic mn. Okay? But it turns out that we can do better than that. We can do better than a brute force approach, and here's the reason why. So here's the motivation for why we can do better than that, or how we can do better.